Okay, in the time while we switched videos, I rearranged the board just a little bit. So here's our picture. The lamina has changed shape slightly. That's due to my artistic talent. Okay, but we're trying to find the x value of the center of mass here. And so what we're doing, remember, is we're just trying to find the moment or the tendency to rotate about a vertical line x equals a. Once we've done that, we'll try to find the a value that makes that moment 0. And that a value will be x bar. So we're going through our usual 4-step process. We had chopped things up into little pieces. For each piece, we had approximated the moment, or the tendency to rotate, about this vertical line x equals a. We did that by choosing a representative point. We used the x value and calculated its signed distance from a. That's our lever arm. Then we evaluated the density at our representative point and multiplied that by the area, and that approximated the mass of each piece. Of course, what we do then in step 3 is we add everything up. And I'm going to leave some room here because I don't want to copy the sum again. Step 4 is going to be taking the limit, and I'm going to write the limit there. So I would have the sum as j goes from 1 to n, sum as I goes from 1 to m, of, let's see, xij star minus a times the density function at xij star yij star. If you prefer to just write pij star to write less, that's fine, times delta a. Okay. So again, we're using a double Riemann sum. I chopped things up this way into m pieces and this way into n pieces, and I and j are the two indices keeping track of which piece we're talking about. Okay, excellent. So that gives me an approximation of the moment, and then step 4 is to take the limit. And so, if I did that, we would have the limit as m and n both go to infinity. And of course, we would basically just take them one at a time. We're not actually doing anything by taking the limit of these double Riemann sums. If we did, we'd have to talk about the rules for when you have to do what in what order. Okay. But we would do that, and that would give us the moment, or the tendency to rotate, about a. Okay. Of course, that's taking the limit of a Riemann sum, so that's just going to be the double integral over the region defined by my lamina of x minus a times the density function dA. So this gives me the moment about A. Now, I don't know what x bar is. Remember, x bar is the x value for our center of mass. So I don't know where it is, but I do know what the moment about the line x equals x bar is. The moment about x equals x bar is 0, because if I support my lamina at this line that passes through the center of mass, I'm going to cancel out any tendency to rotate in that particular direction. So what I can do is I can say I know that 0 is equal to the double integral over d of x minus x bar times the density function dA. And what I'm going to do is I'm going to use this equation to solve for x bar. Seems kind of crazy because x bar is in the middle of the integrand for this double integral. But x bar is a constant. And if I can just use some rules of integration to manipulate my integrals a bit, I know that I can factor constants outside of integrals. So I might be able to actually manipulate this equation to solve for it. So the first thing I want to do is, right now x bar is linked to x because it's inside these parentheses. So I'm just going to distribute the density function to each piece and say that this is 0 is equal to the double integral over d of x. Oh, and I'm sorry, I'm using sigma for the density. I should be using rho. I apologize. I was using sigma, which is the symbol for charge density. I want to use rho, which is the symbol for mass density. Okay, so rho of xy minus x bar times rho of xy dA. But now I can actually split this up into two integrals. So I can say 0 is the double integral over d of x times my density function dA minus the double integral over d of x bar times my density function dA. And now, I don't know what it is, but I know it's constant, so now I can factor that out. So 0 is the double integral over d of x times the density dA minus x bar times the double integral over d of the density function dA. I want to solve for this, so I'm going to take this piece and add it over to the other side. So, coming up here, x bar times the double integral over d of the density function dA is equal to the double integral over d of x times the density function dA. Now to solve for x bar, what I'd like to do is divide by this. Now that has variables in it. I generally try to avoid dividing by things with variables in them in case I'm dividing by 0. How do I know that this quantity right here is not 0? If you need to pause the video to think about it, pause and think. Welcome back. This is just the mass. And my lamina, we're supposing, does have some mass. We can't have a massless lamina. So this is just the mass, so it's okay to divide by it. It's not equal to 0. So I can divide this side by that as well. And so we get that x bar is equal to the ratio of these two integrals, the double integral over d of x times the density function dA over the double integral over d of just the density function dA. Okay. And we can actually abbreviate both of these things. I can just write m on the bottom, where I'm saying m is equal to the mass. Okay. And if I look at the top here, this is actually a moment. Ooh, we're sharing a moment. This is a moment about the line x equals 0, because x would be the signed distance about the line x equals 0. But the line x equals 0 is the y-axis. So I can write this as m sub y. This is the moment about the y-axis. Now do be careful here if you do use this notation. When you're solving for x bar, you're integrating x times the density function. That's the top integral that gets divided by mass. The name of the integral that has an x in it is m sub y, because it's the moment about the y-axis. Algebra students have this same dilemma. The equation of the y-axis is x equals 0. So be super, super careful, and if that's going to cause confusion, just don't use that nickname for things, and you're totally fine. All right, but that's how I would find the x value of the center of gravity. And then I would find y bar in a very similar way. Y bar is just going to be the double integral over d of y times the density function dA over the double integral over d of the density function dA, which is the moment about the x-axis divided by the mass. So m sub x is our moment about the x-axis. Okay, pretty cool. So that's how we're going to find our center of mass. That's the theory. Next video, we'll do an example.